number 1. A hammer is made on swing with the same angular acceleration about the points A, B and C as shown in the figure. If the respective torques required are tau A, tau B and tau C, then we have to compare tau A, B and tau C. We know that when considering first diagram, the heavy end of the hammer is in opposite to point A. Therefore, moment of inertia about point A is the greatest value in given tree diagram. Then moment of inertia of B is less than A, moment of inertia of C is less than B. Therefore, because of point C is at the heavy end, therefore mass distribution is a small value when considering C. Then moment of inertia of A is the greatest value, and we can prepare the order of moment of inertia. The descending order is IA, IB and IC. Now we have to consider the torque required to do the rotational motion. Then we know that if the torque is if the moment of inertia is a greater value, we can't change rotational motion of the object easily. Therefore, if the moment of inertia is a greater value, the required torque also a greater value. Then we can consider tau A is the greatest value, then tau B and tau C. Then answer is 1 for the question number 1. Question number 2. A rotating flywheel of moment of inertia 2 kg cubic meter about its axis brought to rest in 20 seconds by a constant couple of 20 Newton meters acting on wheel. The initial angular velocity of the wheel in radians per second is. We can find the angular acceleration by using tau equals I alpha. Torque given by the couple of forces is given as 20. Moment of inertia of the flywheel is 2. We can find the alpha value. Alpha is 10 radians per square second. Now this is a deceleration. This is an angular deceleration. Therefore, we have to substitute this value as a minus value when using equation. Then I will use the equation omega 2 equals omega 1 plus alpha t to find the initial angular velocity. Final angular velocity is 0 because of the object should be accurate at the final condition. We have to find the initial angular velocity omega 1. Alpha value is a minus value because of there is a angular deceleration. There is an angular deceleration. It is minus 10. Time is given as 20 seconds. Then omega 1 is 200 radians per second. 200 radians per second. Then answer is 3 for the question number 2. Then question number 3. The product angular acceleration times into time has the dimension of. We know that I will consider units. Then considering units, angular acceleration into time. Angular acceleration is radians per square second. We have to multiply by unit of time seconds. We can cancel out one s term, s to the power minus 1. Then unit of product is radians per second. Radians per second is the unit of angular velocity. Then answer should be angular velocity. Answer is 2 for the question number 3. Then question number 4. Stars may be formed when a huge rotating masses contract to small volumes. In such a contraction, how will be the moment of inertia and the angular velocity of the rotating mass change? We know that when contracting an object, its mass spreadness is becomes a small value. Mass spreadness becomes to a small value. Therefore, moment of inertia should be decreasing. And when an object is contracting, there is no an external unbalanced torque. Therefore, we can consider that moment of angular momentum should be conserved. If there is no an external unbalanced torque on an object, the angular momentum should be conserved. Therefore, we can get that I omega, angular momentum constant, but I value is decreasing, therefore omega should be increased. Omega is increasing. Then angular velocity increases. Moment of inertia decreases, angular velocity increases. Then answer is 2 for the question number 4. Question number 5. A wheel rotating at a speed 600 revolutions per second, revolutions per minute, about its axis, comes to rest in 20 seconds. The angular retardation means angular deceleration, in radians per square second is. We can use omega 2 equals omega 1 plus alpha t. Omega 2 equals omega 1 plus alpha t. The object should be at rest when considering final situation. Therefore, final velocity is 0. Initial velocity is given as 600 rpm. We have to convert rpm to radians per second. We know that rpm divided by 60, revolutions per minute divided by 60 equals rps, revolutions per second. It is equals to frequency. Frequency is 1 over period, 1 over t. Period is 2 pi over omega. Then 1 over period is omega over 2 pi. We can equal this part and this part. Then rpm 600 divided by 60 equals omega divided by 2 pi. We can cancel out 10, 25 is omega. It is the initial angular velocity of the object, 25. We have to find the retardation. Retardation means angular deceleration. We have to find alpha value. Time taken to stop is given as 20 seconds. Then we can substitute time as 20. 20 alpha equals minus 25. We can cancel out 20. Alpha equals minus 5 radians per second. Then answer is 4 for the question number 5. Question number 6. Angular velocity has dimensions of. We know that angular velocity is angular displacement theta divided by time. Angular displacement is an angle. For an angle, there is no dimension. Therefore, we can substitute dimensions of angle 1. T is time, dimension of time, capital T. Then T minus 1 is the dimension of angular velocity. Answer is 2 for the question number 6. Then question number 7. Angular momentum of a system is. Statement A. Conserved only when resultant force on it is 0. No. Angular momentum is conserved when resultant torque is 0, not resultant force. We have to consider resultant torque. B. In the same direction as its angular velocity. Yes, we know that angular velocity, angular momentum, torque, and angular velocity, angular momentum and torque are in same direction. We can consider by using the right hand screw law. If the rotating direction is this one, rotation is in this direction, we can get direction of torque, direction of angular velocity, direction of angular velocity and direction of angular momentum in this direction. Therefore, in same direction it is correct. Statement B is correct. Statement C, independent of the mass distribution of the system, angular momentum is dependent on mass distribution. Because of mass distribution, moment of inertia is dependent on mass distribution. Therefore, angular momentum also dependent on mass distribution. Then C is incorrect. Only B is true. Answer is true for the question number 7. Question number 8. A ring, a disc and a sphere, all of same mass and radius, with moments of inertia IR, ID and IS respectively. IR is the greatest value, then ID and IS respectively, about the axis, roll down without slipping on an inclined plane from a given height. If the time taken for the ring, disc and sphere to reach the bottom of the plane are TD, TR, TD and TS respectively, then we have to compare situations. We know that when moment of inertia is a higher value, omega should be increasing slowly. It is difficult to change its rotational motion. Therefore, the rate of increasement of omega means angular velocity, is a small value for the object which has high value. High value means moment of inertia. We can consider that when I is increasing, when I is a higher value, rate of change of omega is a small value. Therefore, time taken to come along the slope is a large value. When omega is increasing slowly, therefore time taken is a large value. Then moment of inertia is greatest value of moment of inertia for the ring, IR, ID and IS. Therefore, time taken to reach also in same order, TR, TD and TS. TR, TD and TS. Then answer is 3 for the question number 8. Question number 9. A flywheel of moment of inertia 9 about its perpendicular axis to the center is connected to a motor. The motor accelerates the flywheel from rest to 600 revolutions per minute. Neglect the friction. The work done on the flywheel is. There is no an external unbalanced frictional torque. There is no frictional torque. There is only one torque. It is given by the motor. Therefore, the work done by the motor is converted into kinetic energy of the flywheel. Therefore, we have to find the kinetic energy of the flywheel. We know that rotational kinetic energy is half I omega square. Half moment of inertia of the flywheel is given as 9 omega value. We know that RPM, revolutions per minute, divided by 60 equals RPS. RPS equals frequency. Frequency equals 1 over period. Period is 2 pi over omega. Then 1 over period is omega over 2 pi. We can use this relationship to find the omega value. RPM 600 divided by 60 equals omega over 2 pi. We can cancel out 10 into 2, 25. It is omega. Then omega squared, 20 squared 400, 5 squared. We can cancel out 2 and 400, 1800 phi square. It is in joules. Then we can consider answer is true for the question number 9. Then question number 10. For identical uniform rods of length L and mass M, sum of which are bent as shown are rotated from rest about its vertical axis. Rods are accelerated until they reach a final angular speed omega naught. Which of the following arrangement requires highest energy to attain its final angular speed omega naught? We have to consider the moment of inertia. Moment of inertia is greatest for the fifth system there because of there is a large mass spreadness when considering fifth one. When I is maximum, moment of inertia is maximum, the work done to change the angular velocity is a higher value. Therefore, higher energy is required for the system 5. Then answer is 5 for the question number 10.